The mass spectrometer. Now that we've shown electric fields and magnetic fields, it's time to show an application that uses both types of fields. A mass spectrometer is used to separate out atoms and molecules based on their mass, and is used to analyze the physical makeup of substances in terms of their relative concentrations of their constituent parts, or atoms, molecules, whatever. This is the first part of a mass spectrometer, the velocity selector. The substance to be analyzed is charged and injected into the left side of the velocity selector. An electric field is directed vertically up. See the blue lines here for electric field. See, this is a negative plate, this is a positive plate. And then you have a magnetic field. It's not just in this one place, but we put it here so we wouldn't make this too complicated. The magnetic field is coming out of the page uniformly everywhere within these two plates. We have a slit on the right side, and the slit's kind of shaped like this, that only lets out particles that are undeflected by the fields. You can see if a particle is deflected by these two fields, it would hit this slit and wouldn't be able to come out. We only want certain particles to get through this velocity selector. Let me draw the edges of the slit here. So if particles come in here with all different velocities, they're going to be affected differently by this combination of electric and magnetic fields. So I only want the ones that have a balanced force. So if I have the electric force and a magnetic force exactly equal and opposite, any particle coming in here with zero force in the y direction will go straight. So let's first of all explain this. The electric field is in the up direction, so the force on a positive charge would be up. Now for the magnetic force on a positive charge, you would use the right-hand rule. The velocity is this way. The magnetic field is coming out of the page, so that means the force through the magnetic field is down. So I have Fe minus Fb equals 0, because I typically take up as positive. The force on a charge is just QE due to the electric field, and it's QVB due to the magnetic field, as long as B is perpendicular to the velocity, which it is, because the velocity is in this plane, magnetic field is coming out of the board. Do a little quick algebra, and I find that the only particles that will go straight through and not be deflected are particles with the velocity that equals the magnitude of the electric field divided by the magnitude of the magnetic field. And you can tune both of these parameters. That's where we get the name velocity selector. These two fields will select only particles with the velocity we're looking for to come straight through. The second and final part of the mass spectrometer is the mass selector. So first, let's show where the velocity selector wound up. This is a piece we just talked about. That's over here. And you here have the charged ions being shot in. Here's your electric field. Here's your magnetic field. Now, for the purposes of this problem, we'll assume that the magnitude of both magnetic fields is the same. Ions reaching the second magnetic field, that's this area here, will all have the exact same speed because of the velocity selector's operation. What happens to the speed of the ions that left the velocity selector here with a certain speed once they're in the mass selector? Think back to the earlier chapter on motion of charges due to a magnetic field. Let's just jump to the conclusion. Their speed stays constant. Why? The magnetic field in the mass selector exerts a centripetal force on the entering ions. This force is perpendicular to their motion at all times. So no work is done on the ions and the speed stays constant. And you can see they're in circular motion here. Again, analogous to the Earth going around the sun. If no work is done, the speed stays constant. Now it's time to solve for the mass of the ions. So let's just talk about the general concept here. We think that a lighter ion, when it hits the magnetic field, the force on the magnetic field, since it's very much lighter, will probably create a tighter circle. A heavier mass will be harder to deflect. So we think it should take a longer time, longer distance before it hits here. Now let's look very carefully at what we're measuring. You see 2r is written here. The radius of this circle, of the motion of the ions, is r, but we're measuring the diameter of how far it hit from here. So whatever measurement you have here, cut it in half for when we use the radius, okay? Just remember to do that. So first we're going to start with Newton's second law. We've got particles in centripetal motion, so FB is mv squared over r. What's the force? What's the magnetic field force here? Well, that would be QVB. So we said QVB equals to mv squared over r. Now before we go to the next step, look at this. Cancel this v out with one of these v's and we solve for mass. Earlier we said that the magnetic field here is going to be same as over here. The reason we did that is because we now want to get rid of this velocity. We can't measure velocity. I don't know how to measure velocity in this. But we will substitute in E over B from the velocity selector. Remember, this guy only let particles with the velocity equal to E over B through. I now put that into the equation, and this tells me I measure the radius, I measure the distance, and recall, if I measure from here to here, I cut it in half to plug in R. I know what the magnetic field is because I said it. I know what the electric field is. I know what the charge on the ions is. I did that using a separate method that we're not talking about here. And that will now tell you the mass of this object, and you'll know the mass of this object. And depending on how many hit here, you can find the relative percentage of those different masses for whatever sample you're analyzing. So, in summary, the various masses of the ions will separate out along the diameter of the mass selector and are calculated by this equation here.